So, yes, I mean, I think we're really well set up after that session this morning, and now we're going to move into essentially the practitioner end-user space and make that link between science and use. So we're going to run a very similar format. We'll have 3 speakers, 20 minutes each, and then we'll have a panel discussion. So the first of those speakers, I hope he's in the room, I'm sure he is. I've seen it, there he is, yeah, Jochen. It's Jochen Hinkel, and please take the stage, Jochen.
Is it? Oh, okay. Well, I'll stand here. I think this isn't better.
Up to you.
I'm fine, thanks. Well, thanks a lot for inviting me to give a presentation here. It's been very exciting. I must say that I enjoyed the early career scientist session yesterday over lunch a lot, and this has inspired me to change quite a bit in my presentation. Actually, I hadn't prepared it anyway, so this is inspired by the discussion yesterday. Let me first say something about the point of departure, which is, I think, quite important because I'm not a sea-level rise scientist, I'm a social scientist, so this is probably a bit unique in this context. And let me explain a bit what my point of departure is for thinking about sea-level rise and coastal adaptation. So I consider myself to be a decision scientist, and decision scientists mainly worry about 2 questions that are related but quite different. So first, there's a prescriptive perspective that we take, and this is the question, how can we best make decision given the information we have, for example, on sea level rise, as well as the preferences of those people that are in the driver's seat, who are affected by the decision or have to make the decision. So that's a very analytical discipline, a lot of math and a lot of, well, scenarios, models, etc. So I think the kind of stuff many of you can relate to. However, there's also a descriptive side to decision sciences, and that's very different. That's trying to understand and explain how decisions and policies are actually made. So this is qualitative social sciences. Our data is from interviewing people, from trying to understand what people are experiencing, etc. And here, I think I need to have a bit of I need to give you an impression on the kind of thinking that is dominating that descriptive field. It's a huge field. It includes political sciences, includes institutional economics, anthropology, etc. So very diverse, very interdisciplinary, and there are different models around how policy and decision-making works, and one model that many of you are probably familiar of implicitly, and Sophie has shown that in her presentation also yesterday, is sort of the so-called knowledge deficit model. And that's very simple. We have a solution that is produced by science, for example, sea level rise scenarios, because there is a problem and people want to know how much does sea level rise. This model is simply empirically wrong. It basically hardly exists, in particular not in our domains. I mean, if you look at, I don't know, material sciences, of course, sometimes stuff is developed upon an explicit knowledge gap in industries, but generally it hardly exists. But it's very prominent. What the sort of more dominant view on decisions is, and this is now according to the multiple streams framework of Kingdom, which is one of the biggest theories we have nowadays in political sciences explaining policy making. There are a couple of others, but I'll just take this one because it's very big, prominent, thousands of people around the world applying that every day, if you want, in their research. Here it shows that we have separate streams. We've got 3 streams with separate people working in those streams, and One, we have the problem stream. So this is the real world. This is administration facing some problems, people, society facing problems, for example, flooding. We have the politics streams that runs independent from the problem stream. This is about interests, where people try, the politicians try to fight against each other and dominate, exercise power, and get what they want according to their core beliefs, the policy beliefs, and the interests. Then we have the solution stream. That's basically us, the researchers working on solutions such as sea level rise scenarios. And usually everything we do goes into the bin. Former version of that model, the first version, has been called the garbage can model of policy making. And that's not polemic, it's just empirical evidence. Excuse me. Policy happens, policy change happens if those streams are somehow coupled. And one way of coupling those streams is what is called focusing events. If you think about coasts, it's often a flood. It's a disaster that changes the course and makes the politics stream aware there is a big issue. And that doesn't have to be exactly in the same place. If you think about Fukushima was the end of nuclear power in Germany, so it can be around the world. This couples those streams, and then there's an opportunity actually for the solution stream to inform the politics streams. But how it usually works is politicians, they have an interest, they have a belief, and they're selecting these scientific studies that undercover their belief, that support their beliefs. There is, however, an also opportunity to influence that, and one concept which is very prominent in current research about policy is the concept of policy entrepreneurs. So those are people who are moving between the streams, can couple streams, can influence people. So it's often about individuals, charismatic or powerful individuals, that can actually bring solutions into the politics streams. I leave it there. Keep that in mind if I'm now going to speak about the IPCC sea level rise scenarios and how they're being taken up in decision making. Let me first present sort of a very rough view of how IPCC sea level rise scenarios were communicated in the IPCC report. You probably know that stuff, so I can go through that rather quickly. So this was IR4. 60 centimeter was the worst case scenario according to the table that was published in the SPM. There was an important notice here within the table that some processes were excluded, in particular the dynamics, the dynamical discharge. If you then read the sea level rise chapter, it sort of told you, okay, we've had an increase by an order of magnitude of the ice sheet mass loss during the last decade. It also said that it might be just a transient phenomenon, but if we upscale that, it will be, I don't recall, 17 centimeters, I think it was. If we upscale the acceleration, it would have been 17 additional centimeters by the end of the century. But the justification for not putting that into the table was, well, we cannot assess the likelihood. From a decision-making point of view, or from a prescriptive decision-making point of view, that's not really understandable, because if you want to make a decision, you need all information available. Just a partial representation misguides. We don't need probabilities to make decisions, but we need all information. RR5, there we had somehow a similar situation. I mean, at least from my point of view, we had this graph and we had a footnote saying, again, that the dynamical contribution from Antarctica was excluded because it could not be assessed, and possibly that's then going to add a couple of decimeters to the upper numbers of sea level rise. It also explained that and motivated that. Now we have sort of medium confidence information. Those are the physics-based models, which happen to exclude some of the processes that are relevant, in particular for the rapid melting, but we cannot include them. And it also said there is low confidence information, such as at that time the semi-empirical models were very prominent. Well, there was this Pfeffer et al. Paper on the physical constraints, reckoning, I think, 2.4 meters of possible ice, overall sea level rise, including the contribution of Antarctica during the 21st century, etc. So there was a lot of stuff that was, again, excluded from the figure. Again, from a decision-making point of view, that's not a good idea. We need everything you know in order to make decisions. Just putting stuff in a footnote doesn't work. Footnotes are hardly perceived. We'll get to that. RR6, a slight improvement. For the first time, we have low confidence scenarios displayed in the same picture as sort of the medium confidence scenarios. And while the chapter explains that to some detail, actually now a new paper has come out by Kopp et al. That explains it to a better degree than it is explained in RR6. It's actually very difficult to understand. I haven't met many people who understood actually what was happening there, even within the geophysics sea level rise community. But anyway, we've got different sets of scenarios, low confidence scenarios that then address the ice sheet contribution by, for example, the expert elicitation by Bamber et al. 2019. And we have also the Conto and Pollard model being part of another set of low confidence projections. That includes the MICI, the marine ice cliff instability. So from a decision-making point of view, this is also not very satisfactory because you still sort of, you have got a main thing here and then a little dashed line around the corner. And to be honest, also, in the perception, I haven't really found many people who pick up on this low likelihood trajectory, even though it's right in the picture. Anyway, I think this is a great improvement, but we can do better. The main point of my talk is now to give two examples how this was used in actual policy and decision-making. And mind, those are two out of many possible examples, so I don't want to claim anything universal by those two examples, but I think it's still illustrative. I'm taking two different examples, the Maldives, where I have worked since almost 20 years, and Germany. I'm German, so I have also a bit of exposure to what's happening in Germany, so I have first-hand knowledge of those cases. So the RR4 stuff actually influenced the Maldives. There was land reclaimed, and a massive piece of land was reclaimed, the island of Hulhumale, which is the island neighboring the capital island of Male in the Maldives, and there is a great need for space. And this island was actually reclaimed at 60 centimeters higher from the normal height of the capital island. And supposedly, there are different stories, but some stories point towards this 60 centimeters coming from RR4, because that was the highest number under the worst-case scenario in the table. Then IR5 influenced also a bit the policy. The land reclamation guidance was issued, and they took the 1 meter. So this was, again, the worst case RCP 8.5 scenario, the upper bound of the likely range. That was taken together with the tidal range in the Maldives, which is 60 centimeters, as sort of an indication at which height future islands should be reclaimed. This recommendation is not binding, and it's also often not complied with. I mean, there's a lot of land reclamation ongoing in the Maldives, so there are many examples where this has been ignored. And interestingly enough, there is up to now no other policy in the Maldives that considers sea level rise. We've done a detailed review of that. That may surprise, and I'll try to explain. Furthermore, RR6 was basically ignored. I mean, people read it, but it was simply nothing new. Same of the old story. I must say the Maldives have very strong expertise in terms of understanding IPCC because people are involved in the IPCC reports and writing the IPCC reports. People are very strongly represented in the UNFCCC negotiations. So those are experts, if you want, in terms of IPCC jargon. A couple of explanations. So why was the number directly taken from the table of the SPM, the 0.6 meter? Well, it's easy to legitimize. If you can say, look, this is the number of the IPCC, then you have a good legitimization which prevents you from being attacked from your political opponents. It's also that there is only one number. I mean, it's the table, no matter what the footnotes are or what's written in the chapter, etc., because you cannot defend anything what is written in the chapter if you have a political debate. You know, it's just this one number, more is not possible. I've also worked in many other countries where this was a big issue. Governments want the exact IPCC scenarios, even though we were making strong arguments, look, I mean, if you want to build a massive infrastructure project, it's better to consider some higher scenarios that are also possible but less likely, but they want the IPCC stuff. And I think this is a big issue. How am I doing in time, actually?
That's a good question. 5 minutes?
5 minutes left. Okay. Why is there no adaptation policy in the Maldives? Well, it's simply not the political priority. Development is the priority, and they've had rapid GDP growth of around 10% for the last 15 years. Land reclamation is cheap. Everybody wants land. They've got their own dredging boat to do that. It's a bit like a money printing machine in an urban context. So many of us think of the Maldives as being, you know, palm trees, sunshine, etc. But this is the reality of most people on the Maldives because most people live in the capital center islands of Male and Hulu Male. And imagine reclaiming land on a reef flat, 2 meters deep. If you can then build high-rise buildings on top of that, it's simply a money-printing machine, no? I mean, it's very cheap. And if sea level rise comes, we can simply reclaim another island that's a bit higher. So people are risk-tolerant. They're not so risk-averse as people in Germany, for example. And there's simply time. There's also time to upgrade. And then a final point, and there was a question, the panel before on that. It's really not sea level rise. What's the biggest threat, future threat? It's the waves. I mean, flooding is caused by waves currently that are overtopping the islands. And the issue is the wave heights are dramatically reduced by the reef flat. So a wave is 3 to 4 meters outside of the reef flat. It travels towards the island. When it arrives, it's only 1 meter or half a meter when it hits the island. Now, if the corals die, and there's a lot of indication that this is going to continue, then this natural protection will be gone, and you'll be facing high waves hitting the island. So you move from half a meter to 3 meter within 20 years. So what does another 30 centimeters of sea level rise play a role in that? I mean, this is a bit exaggerated, but it's simply the waves. That's the current problem, the extremes. Let's turn to Germany, and I think I'll then leave it there. I'll skip the rest of my presentation. DAY4 was perceived but ignored. They took Rahmstorff, the semi-empirical modeling stuff, as design height for dikes, but not really as design height. It's more like as an upgrade allowance. So this was the original dikes before sea level rise, was in the media. In 2000 already, it was decided each dike we upgrade, we build half a meter higher, and we build a wider crest. And this wider crest then allows us, in future times, depending on how sea level turns out to be, to add further upgrades up to 1.5 meters height against, well, possible future sea level rise. IR5 was ignored, and IR6, well, not really much happens on that. I mean, it's been picked up and it's reported in the new master plan, but actually there's also a statement saying, well, all these low confidence scenarios, they're not really ready to be used for planning, so let's ignore them. A couple of explanations. So why the Rahmstorff 1.4 meter? Well, we are risk averse. We've been protecting against the sea for a long time. There's a high expertise in the public administration. They think they don't need the IPCC report. They read the literature anyway. And there's a low risk tolerance. So, I mean, if we think about the future, let's take the highest number and then we are safe. IR5 was ignored simply because it didn't fit in the policy cycle. The master plans, they are renewed every 12 years. And so if IPCC report comes out in the meantime, doesn't matter. IR6, why was that not picked up? I think it's really two things. I mean, we have a tradition in Germany of protecting against sea level rise, or fighting against the sea. And that is also underpinned by the public sort of communication that everybody is safe. Always safe. There is no risk. There was a severe flood in the 60s. Ever since, people are safe, and this will never happen again. So they're basically also afraid of those high sea level rise numbers making people uneasy, and they would have to change the narrative. And it's really a century-old thing. I mean, there's a saying in Germany, God created the world, but the Frisians created the sea, because they've been building into the sea and protecting themselves for centuries. I guess I'm done. Before I can come to my ways forward, how much time do I still have?
I'll give you 2 minutes.
2 minutes, thanks. Okay, I'll be quick. We have to acknowledge the political nature of politics. I think I made that point. We also have to acknowledge the diverse context. Resource-rich countries can read and do their own analysis. Resource-poor countries are bound to stick to whatever is on the front page of the IPCC report. We have to acknowledge the diversity of decisions. And actually, it's important to start from the decision. A lot of sea level rise scenarios are produced without thinking about decisions. They're just sort of, let's communicate sea level rise. But if you want to do something useful for adaptation, you have to start all reasoning from the decision and the context. And actually different contexts and different decisions require different kinds of frameworks and also different kinds of scenarios. There has been a lot of talk about the high-end scenarios. I mean, we saw Roderick's presentation. I think this has been accepted that some kind of decision framing needs high-end scenarios. Let me talk about something else that is not very prominent in the literature, and this is actually my last slide, and those are learning scenarios. So what you see here, it's the typical scenario where we have, for example, the likely range in 2080 seen from today. That assumes we decide everything today. However, as you've seen in my examples, most decisions are multi-stage. No, we have decision points, we upgrade dikes in the future, we build in flexibility into today's world, and hence we also need to know future projections of sea level rise in the sense that I might observe a certain amount of sea level rise in 2050, and I need to know, starting from 2050, what is the likely range for 2080? That's missing. We don't have that. There is a way to generate that, and we also need to know that for other points in time, there's a way to generate that from, for example, probabilistic projections. We've just done so for RS6. It's accepted by Future Earth. And essentially it boils down to, instead of having probability distributions for each point of time, as you have in the probabilistic scenarios, that's the yellow stuff, you have a tree form of scenario, and from any point, let's say from 2070, you have the probability of going to, for example, 2100, then this range would be possible. So we need those intermediate ranges for advanced decision-making, such as real option analysis, and also for adaptation pathways, etc. Sorry, I needed to be quicker. Thanks a lot.